Mrs. Bodechon here. So today we're going to be talking all about specific heat math. So let's look at our equation. Our formula is Q equals Cm delta T. Now let's talk about each one of those variables and the units for those. So we're looking at Q. Q is just a change in thermal energy, and it's actually measured in joules with a capital J. C is a specific heat of the material. Now every material or substance has its very own unique specific heat. So you're going to have to look up this information either in a data table or it may be provided in the question that you're given. So for example, you can see we have a list of materials here, and then right next to it, their specific heat. So you'll have to find exactly which one you're looking for to solve your math problem. The units for these are going to be joules per gram degree Celsius or joules per kilogram degree Celsius. But I can say for us, we will be working with this one, joules per gram degree Celsius. M is for mass, and it's either going to be measured in grams or kilograms. We're going to be working with grams today. And then there's delta T, which is just the change in temperature. So really what that's saying is the final temperature minus the initial temperature. It is measured in degrees Celsius, but I want to make sure that we understand what this is actually saying. So your final temperature is the temperature that you finish with, okay, your end with, and you're going to subtract that from your initial temperature, which is the temperature that you start with. So it does seem backwards, right? It seems like it's completely in reverse, but make sure you put your numbers in the right order or you will not be getting the correct answer, okay? So let's go ahead and try out a quick example. So what material will heat up and cool down the fastest? If you're looking at this data table, what is this question really asking us? It's really asking us what material has the lowest specific heat, right? So in other words, we're just looking for the lowest number on this data table, and that's going to be lead. So if you look at lead, it does have 0.129 joules per gram degree Celsius, right? So it's the lowest number on this data table. In other words, it has the lowest specific heat, and it will change temperature with the least amount of energy applied. Now this one says, what material will heat up and cool down the slowest? So this is just the opposite, right? So we're really looking for the highest specific heat on this data table. And if you look through this, you're going to see that it is water. And water has 4.18 joules per gram degree Celsius. So it's definitely the highest number, highest specific heat. Water will take the most amount of thermal energy to heat up or cool down. Okay. Now let's try to get into some math, all right? So a 50-gram silver teacup cools from 60 degrees Celsius to 20 degrees Celsius. What is the change in its temperature? So it's only asking us for delta T. So we don't have to worry about our whole equation right now. Let's just focus on delta T. So remember that equation is the final temperature minus our initial temperature. Well, if we read the question again, it says it went from 60 to 20. So 60 is where we started and 20 is where we ended. But we have to flip-flop these, right, in order to solve correctly. So here is what we know. We know our initial 60 and we know our final is 20. So if we substitute that in our equation now, you can see that we're going to put the 20 first because that's our final, and we're going to subtract that from our initial temperature, which was 60. So we're going to end up with a negative 40 degrees Celsius. It's okay to get negative numbers. In fact, that negative number just means that you lost or removed heat energy or thermal energy. And does that make sense? The cup cooled, right? It's saying it cooled off. In other words, it removed some heat. So that negative number does make sense, okay? All right, so if we have the same silver teacup, what is the change in thermal energy? Now it's asking us to go ahead and just do the full equation, right? So we're going to go ahead and use our Q equals Cm delta T in order to solve this. To find that change in thermal energy, which is Q, we need to know a couple of things from our problem. So we have our delta T that we already solved was negative 40 degrees Celsius. Our mass, it says right here, is 50 grams. So we can go ahead and notate that. And now we need the specific heat of silver. If we look at our data table, we can find silver, and it is 0.233 joules per gram degree Celsius, and we went ahead and notated that as well. All we have to do at this point is substitute in our variables and then solve with our calculator. So if you go ahead and you just write Q equals, we're replacing our C with our 0.233 and our M with our 50 and our delta T with the negative 40 and multiply that across, you end up getting a negative 466 joules. Remember, Q is measured in joules because it is a form of energy. And yes, your answer should be negative because this problem is talking about cooling off or removing that heat, right? Or that heat energy, the thermal energy. All right, let's try another one. If the temperature of a 35.5 gram of ethanol increases from 30 degrees Celsius to 88.8 degrees Celsius, how much heat has been absorbed by the ethanol? The specific heat of ethanol is 2.44 joules per gram degree Celsius. So this one, we don't have a data table. It gives us our specific heat right away, and it's telling us it's increasing temperature, right? So it says increases. So we know we're going to end up with a positive number now. If we ended up with a negative number, we did something wrong because we're increasing the temperature, we're improving and gaining that thermal energy. So we're going to use the equation, same one we've been working with, the Q equals Cm delta T, and we're first going to find our delta T, okay? So final minus initial. If we look at everything that we're given from our problem, you can see that 35.5 grams is our mass. The next number that we can see on here is going to be our 30 degrees Celsius, and it goes to 88.8 degrees Celsius. So that is our final and initial temperature here. And then we already wrote down our specific heat that we didn't have to find in a data table this time. They just gave it to us, which is awesome, right? So let's go ahead and get delta T. We're going to do final minus initial. So we're looking at 88.8, and we're going to subtract that from our 30 degrees Celsius, and we end up with a positive number, 58.8 degrees Celsius, which means we're on the right track, right? We're adding that thermal energy in our word problems, so we know our answer should be positive so far, and it is, okay? Now we're going to go ahead and substitute in our variables and solve. So we're going to substitute in C. Our C was at 2.44, and here we have it. We're going to substitute in our M. That's 35.5 right here, and we have it. And our delta T, which we just solved for, and that is a 58.8 right here, and we have it. And all we have to do is multiply across in your calculator, and you end up getting 5,093.3 joules. Don't forget to add that joules, a capital J at the end, because Q is thermal energy, okay? All right, let's try one more using a data table this time. So if the temperature of 50 grams of water increases from 23 degrees Celsius to 47 degrees Celsius, how much heat energy has been absorbed by the water? So we are going to be using the same equations that we've been working with the whole time. Let's first write down our given. So what do we know? What variables can we start to identify, right? So if we look at our problem, we first come to 50 grams. 50 grams is going to be your mass. So go ahead and write down your mass is 50 grams. Now we can see our temperatures right here. It says we increase. So we know we're increasing thermal energy. So our answer should be positive, right? So if it's not positive, we did something wrong. We need to go back and check our work. So we're going from 23, that's our initial, and we're going to 47. So that's going to be our final temperature. So go ahead and notate those. And it's talking to us about water. Okay, so now we have to go to our data table because it didn't tell us the specific heat of water. So now we have to go to our data table, look for water, and see what our specific heat is. And it is right here at 4.18 joules per gram degree Celsius. So go ahead and notate that. And we're ready to go ahead and substitute and solve, right? So all we have to do is solve our delta T first. So we're going to take our final temperature, 47, subtract that from our initial temperature of the 23, and we get 24 degrees Celsius. Now we're going to substitute in everything we know and solve in our calculator. It really is as simple, you guys, okay? So Q equals C. Our C is going to be that 4.18, and we'll go ahead and put that in. Our M is 50, put that one in. And our delta T we just solved for is at 24. And all we do is multiply all of those numbers straight across. If you get it in your calculator, it is 5,016 joules. Again, don't forget to put that capital J at the end because it is a change in thermal energy. Our answer is positive. We increase that thermal energy, so we know that we are on the right track or correct, okay? Thank y'all. I hope this was helpful. So if specific heat or specific heat capacity is still challenging to you, I do have a video just over the basic concepts of it. Go ahead and click and watch that video, you guys. I hope that this was helpful. I'll see y'all later. Bye, everybody.